Hi, good day to you, and welcome to my channel where I tutor you in science for free. The topic in this video will be radioactivity. This word gives you the feeling that if you're exposed to it, you'll get some burns, you'll get illnesses, and it's always related to the atomic bomb. In this chapter, we'll discover what is this all about. So radioactivity, by and large, is generally the decomposition of an atom. So before we dive deeper into what radioactivity is all about, we need to understand how the atom is like first. So this is a brief introduction of the atom. You can go and find out more of it in the previous videos. An atom is made out of three particles: proton, neutron, and electron. Electrons are the one that moves around a nucleus, and a nucleus is in the center of the atom where there is a congregation of particles, and the protons and neutrons will hang around there. Protons are positively charged, electrons are negatively charged, and neutrons do not carry any charges. So these three, protons, neutrons, and electrons, are subatomic particles. So proton number, like mentioned in earlier videos, is like the class register number of the atom or the element. So no two elements will carry the same proton number. Proton numbers are specific. And in an atom, total positive charge equals the total negative charge. So the proton number represents the number of protons in the atom. It also represents the number of electrons in the proton, and this is represented by the letter Z. Atoms also have this larger number called the nuclear number, also called the mass number. It is represented by the letter A, and particles that make up the nucleus are called nucleons, and nucleons consist of protons and neutrons. So nuclear number is the total number of protons and electrons, and they represent the mass of the atom. It's also commonly known as the mass number. And so the number of neutrons can be determined by having the big number minus the small number. So the mass number minus the proton number, you will get the neutron number. So in the chapter of radioactivity, a nucleus that contains a particular mass number is called a nuclide. So this is just to get you familiar with more vocabulary. So this is how a notation is arranged: superscript for mass number, subscript for proton number, and the chemical symbol that can be found from the periodic table. And in recent years, there is this change where the numbers are found, whether the big number is on top or below. You don't have to worry about it too much. You just have to know the bigger number is the mass number, the smaller number is the proton number. This gives rise to our next topic called the isotopes. It's also mentioned in the previous video. You can go and check them out. We will just run through briefly. Isotopes are atoms of the same element, but they just contain different number of neutrons, so they carry a different number of mass. Example over here, we have carbon, the common one, which is carbon 12, and also carbon 13, carbon 14. These are found naturally, so therefore, but these are a little bit more rare. The carbon 12 one is the common one. And because it's so common, that is why atoms have their weight based on 1/12 of a carbon 12 atom. So that is the more stringent, the more scientifically accurate definition. And because isotopes have the same number of electrons, they'll have the same chemical properties. Remember, chemical reaction is a game involving exchange of electrons. Nuclear reaction, in this chapter we'll be exploring, is the exchange of nucleons. So we'll be talking about the basics of an atom. Now let's go through what is radioactivity. Imagine when you were younger, you were playing with cards or little dominoes. You stack them up very high. Up to a certain point, it starts to collapse back on itself. That is generally how the concept of a nuclear decay happens. When an atom is too large and it cannot really hold on to its own weight, it will start to decay. Nuclear decay happens, random process by which an unstable atomic nucleus loses its energy by emission of electromagnetic radiation or particles. Nuclear decay is also known as radioactive decay or radioactivity, where the atoms contain unstable nucleus. The particles start to fall apart or energy start to dissipate, and these events are spontaneous and in random direction, so it's not possible to predict when it will happen or where it will go. So there are three ways a unstable nucleus dissipates its energy, and that's through emission of alpha particles, beta particles, and gamma rays. So an alpha particle contains on 2 protons, 2 neutrons, which is also identical to a helium nucleus, and it has the highest ionizing effect. What does this mean? Ionizing effect means it is able to force an electron out of the material it comes into contact with, thereby producing an ion on the recipient material. Okay, so this is what makes it dangerous. It causes damages to the particles it comes into contact with. However, it has the least penetration ability, so it's easily absorbed by a piece of paper. The next one is the beta particles, and that is just a fast-moving electron, and its ionizing effect is slightly lesser and is absorbed by a few millimeters thick of aluminium. Gamma rays, on the other hand, are just electromagnetic radiation, where an unstable nucleus dissipates its energy out. It has the lowest ionizing effect. However, it has the greatest penetration power, which only can be stopped by several centimeters thick lead. And so when we are talking about this decay, it's pretty simple mathematics. So over here, if you're talking about a particle, a nucleus that has these values, if it emits an alpha particle, then the resultant is just this. So it's just one minus the other, you'll get the answer. If it emits a beta particle, the reaction will just look like that. And lastly, for gamma radiation, it usually happens together with alpha decay or beta decay. And this is how the equation is done. You usually just show this as a notation. And next, radiation is actually all around us. It happens in food, from materials, from living things, from space. And generally, they have very little effects on us. So earlier, we talked about ionizing power or ionizing radiation, which is having high energy that can push off electrons or knock off electrons from the atoms of the recipient material. So things like high energy UV rays, X-rays, gamma rays are examples of ionizing radiation. It has the ability to do that, so it's not good to have such long-term exposure, as it does cause damages to yourself. And background radiation refers to nuclear radiation in an environment where no radioactive source has been deliberately introduced. So it's generally found in nature that we encounter every single day. And here are some common sources for artificial radiation and natural radiation. And talking about ionizing radiation, we can measure it using this device called the Geiger counter. So the SI unit of radioactivity is becquerel. 1 becquerel is 1 disintegration per second. And there are other units of radioactivity like the sievert, but you don't have to know too much into detail. Just know that it's like pounds and kilograms for weight. Sometimes radioactivity also has its different units. So we have been talking about an atom disintegrating, losing a part of itself. So there will be a period of time where the atom will lose so much of itself, it becomes half its original weight. This period of time is called the half-life. It is the time taken for half the nuclei to decay. And this is a very significant finding or characteristic or attribute of a radioactive nucleus, because the time taken for the nuclei to decay to half its weight is the same. It is fixed. So if originally it's at 120, it takes 8 days to decay to 60. From 60 to 30, it takes another 8 days. From 30 to 15, it takes another 8 days. So this is why we must understand the half-life in order to learn and be able to backtrack, or rather we call it interpolate or extrapolate, to predict forward how long does it take to decay to a certain value. And this is depicted on a decay curve, which can be drawn very simply just like that. So we've been talking so far about nucleus decaying. What about merging and splitting? In this case, nuclear fission and nuclear fusion. Fission sounds like fission and fusion sounds like a fuse. So division is to split something into more pieces, and fusion is to take several pieces and put it into one. So firstly, we talk about nuclear fission process, whereby nucleus splits, releasing huge amount of energy. And so how this works is having a large nucleus, like a uranium nucleus, and what happens next is when a neutron is so small, it can get close to this large giant mass of positively charged nucleus. So a neutron is being fired into a large mass, a large nucleus. It splits, thereby releasing more neutrons, and these neutrons will go further to split other large nuclei. And this process continues as a chain reaction, and each of these split releases a large amount of energy. And so the equation is similar, just some very basic mathematics. Make sure that all of them add up to each other, then that's about it. In fission, there are several possible fission products, so it's not fixed to a formula. So to check the total number of particles and the relative charge should be balanced in a equation. So fusion, on the other hand, is a process where two light nuclei combine to form a heavier one, releasing large amounts of energy. This is another example, a very simple mathematics behind it. Just make sure that everything checks out and you'll be fine. So in nuclear power plants, nuclear fission is used because it sustains itself as a chain reaction, heating itself, generating more and more fission products, more neutrons. Thereby the energy release is used to turn turbines and generate electricity. Nuclear fusion also produces energy, but however, a lot of energy is required to force two positively charged nuclei together. A lot of energy needs to be overcome these repulsive forces in order to make it happen. So nuclear fusion can take place in the sun because there is sufficient energy over there. It's very hot. And so we come to the last part of this chapter. We're talking about applications of this radioactivity. And so there are medical users, there are safety users, geology users. Gamma rays used in the detection of tumors. Beta particles are used to treat certain illnesses. However, for this, there is a long half-life, so therefore only a small quantity is needed. So in terms of safety, we use it for killing microbes in food. So similarly, having long half-life, small quantity is required. And it's also used to sterilize medical equipment. All of these applications are used with the similar concept of trying to destroy certain kinds of cells based on the amount of energy and the particles that they are emitting out of their nuclei. And if we are talking about applying the use of half-life, there's this species, uranium-238, half-life of 4.5 billion years. Therefore, it can use to determine the age of certain rocks based on their decay curve. And very common is the carbon dating. Carbon-14 is being used, and because most living things contain carbon as their central element of building blocks. For most biomolecules, carbon dating is thus used for the estimation of the age of a certain fossil. If we're talking about applying its penetration and ionizing powers, alpha particles used in smoke detectors. How this works is when smoke enters the detector, it blocks the alpha particles from touching its sensor. And when that happens, the sensor is not receiving alpha particles and it will sound off. Beta particles are used to measure thickness of materials. This is very important in things like train tracks when they are doing maintenance work. And because of this, its powers, its ionizing powers, penetration powers, there are hazards when you going too near to these species of particles. They can, of course, cause cancer. Not only is it able to kill cancer cells, it can also cause cancer. When a healthy cell is exposed to these sources for too long, certain gene is being damaged or certain gene has been mutated, it can lead to cancer. So firstly, to protect ourselves, we limit contamination. We leave the area immediately, remove outer layer of clothing, and wash it off appropriately. Next, of course, reduce exposure. Treat these sources, radioactive sources, as per how the safety instructions is directed. Reduce exposure time, increase distance, shielding, and proper storage. And because this is an old chapter, we go back in history. The last time this was tested was in 2013, so 2014 to 2023, radioactivity was removed. Therefore, there will be no sample questions. I figured that it's more efficient to produce a video now rather than wait for next year just for a couple of questions. And I hope you have enjoyed the whole journey in physics. I've come to the end of the physics chapter. And if you have been following me, I've completed the whole biology, the whole chemistry topic, and now I've completed the whole physics topic as well. I'll be going to more in detail on tips and tricks on how to learn and also how to teach and coach others. So stay tuned, more exciting things are in the pipeline. I will see you when I see you. Thank you for your support all this time, and goodbye. And that is all for today. Hope you enjoyed this video. Give it a like and subscribe. Share it with somebody that needs to see this. And I will see you in the next video. Bye.